Hello, it's Celeste. You've had such a long day, haven't you? Your mind is probably still racing with thoughts. But tonight, we're going to let all of that go. Tonight, I want to tell you a story about the most powerful telescope humanity has ever built, and what it revealed when it looked deeper into the universe than anyone thought possible. The James Webb Space Telescope peered 13.5 billion years into the past and found something that shouldn't exist. Galaxies filled with hundreds of billions of stars, shining when the universe was just a baby, just 400 million years old. Our physics says they cannot exist. They're too massive, too ancient, too perfectly formed. Yet there they are, burning in the darkness of deep time, defying every equation we wrote. So close your eyes, get comfortable, and let your breathing slow down naturally, and drift with me into the deepest mysteries the universe has ever shown us. The first images from the James Webb Space Telescope arrived on Earth in July 2022. Scientists expected beauty, certainly. They expected clarity. They expected to see further than ever before into the cosmic past. What they did not expect was to find their fundamental understanding of the universe completely shattered within just weeks of the telescope opening its golden eye. Let yourself relax deeper. There's nothing to worry about. Deep within those first stunning images lurked galaxies that should not exist according to everything we thought we knew. Massive spiral structures containing hundreds of billions of stars appeared in regions of space so impossibly ancient that light from them had been traveling for over 13 billion years. These galaxies existed when the universe was barely 400 million years old. A cosmic infant, by any reasonable measure, still learning to form its first structures. The scientific community had spent decades preparing for Webb's launch. Engineers carefully folded 18 hexagonal mirror segments into an intricate configuration that would somehow survive the violence of a rocket launch. Technicians painstakingly tested every single component against the extreme cold of deep space. Mission planners calculated complex orbital trajectories to position the telescope at a special point called the second Lagrange point, and 1.5 million kilometers from Earth, where the gravitational influences of the Sun and Earth create a stable pocket in space. The total investment exceeded $10 billion and consumed 25 years of development. All of this preparation aimed at one ambitious goal: seeing deeper into cosmic history than any instrument had ever seen before. Your breathing is becoming slower now, more rhythmic. Nobody prepared for what that deeper vision would actually reveal. To understand why this discovery both terrifies and excites astronomers in equal measure, you must first grasp how galaxies are supposed to form according to our models. Standard cosmological theories describe a slow, deliberate process spanning billions of years, not hundreds of millions. After the Big Bang, a matter distributed itself almost perfectly evenly through expanding space. The universe began as a nearly uniform soup of hydrogen and helium, with density variations so incredibly small they measured barely 1 part in 100,000. These tiny variations, quantum fluctuations, stretched to cosmic scales during the first fraction of a second of existence, created regions where matter was just slightly denser than average by the tiniest amount. Gravity went to work on these dense patches with patient persistence. Over hundreds of millions of years, matter gradually fell inward toward the densest concentrations, pulled by invisible gravitational hands. First came small clumps, containing perhaps 1,000,000 solar masses. Then larger structures slowly accumulated as these clumps merged together over eons, and dwarf galaxies formed first, containing only millions of stars scattered through dark matter halos, spanning thousands of light years. Feel yourself drifting, floating, peaceful. These cosmic building blocks were supposed to merge over billions of years, gradually assembling the massive spiral galaxies we see in the universe today. Our own Milky Way required approximately 10 billion years of merger activity to reach its current impressive size of 400 billion stars. The process was supposed to resemble construction more than explosion. Small pieces combined into medium pieces combined into large structures. Large structures continued growing through ongoing mergers and gas accretion over vast stretches of time. The mathematical models describing this process were elegant and beautiful, and the calculations worked perfectly. Computer simulations running on the world's most powerful supercomputers produced virtual galaxies that matched observations across cosmic time. Every major telescope seemed to confirm these predictions. The Hubble Space Telescope observed galaxies at various distances corresponding to various ages, and the size progression matched theoretical expectations almost perfectly. Galaxy formation appeared to be a solved problem, understood in sufficient detail that astronomers confidently predicted what Webb would find when it looked even deeper. They predicted that the earliest galaxies would appear small, irregular, and primitive. Clumps of gas just beginning to form their first stars. Blue smudges marking the locations where cosmic structure was only starting to emerge from primordial uniformity. The first 500 million years of cosmic history should show a universe still assembling itself, not a universe already filled with mature galactic structures. Your mind is so calm now, drifting through cosmic time. Then James Webb looked deeper than any instrument had ever looked before, and everything changed. The galaxy designated Glass Z13 became the first sign of trouble. This galaxy appeared in Webb's initial deep field observations, captured during the telescope's first weeks of scientific operations. Light from Glass Z13 had traveled for approximately 13.4 billion years before entering Webb's golden mirrors. When astronomers calculated its mass, using standard techniques that had worked reliably for decades, the numbers made absolutely no sense. Glass Z13 contained billions of stars, not millions like the primitive dwarf galaxies models predicted, but billions, packed into a structure that had somehow formed within just 300 million years of the Big Bang. 300 million years. Consider what this time frame means in cosmic context. The universe itself is approximately 13.8 billion years old. 300 million years represents barely 2% of total cosmic history. In human terms, this is like a newborn baby, appearing fully grown and running marathons within the first week of life. The developmental stages that should precede maturity simply did not occur. The galaxy appeared in its mature form almost immediately after the universe began. Let this impossibility wash over you. So peaceful, so mysterious. But Galaxies 13 was just the beginning, and as Webb continued observations throughout 2022 and 2023, more impossible galaxies emerged from the darkness of deep time. Each new discovery pushed the boundaries of what physics supposedly allowed. The massive galaxy cluster, called Abel 2744, provided some of the most dramatic revelations. This enormous foreground cluster sits approximately 3.5 billion light-years from Earth, containing thousands of galaxies bound together by gravity. Webb used Abel 2744 as a gravitational lens, exploiting Einstein's prediction that mass bends the very fabric of space-time itself. The cluster's enormous gravity, equivalent to several quadrillion solar masses, warped space-time so severely that light from background galaxies curved around the cluster like water flowing around a stone, and this gravitational lensing magnified background galaxies by factors of 10 or more, revealing structures that would otherwise remain invisible, even to Webb's powerful instruments. The cluster acted as a cosmic telescope, extending Webb's already unprecedented reach even further into the ancient universe. Behind Abel 2744, astronomers found galaxies that existed when the universe was merely 3% of its current age. These were not primitive collections of gas and dust struggling to form their first stars. They were fully developed structures with complex shapes, containing stellar populations that implied generations of previous evolution. Your consciousness floats through this ancient cosmos, timeless, eternal. One galaxy designated Jedia's GS Zgaz 13-0 contained approximately 400 million stars crammed into an area smaller than our Milky Way's central bulge. Its stellar population showed unmistakable signs of multiple generations of star formation, meaning that stars had formed, lived their entire lives, died in spectacular supernova explosions, and seeded new stellar generations with heavy elements. All of this cosmic cycling had occurred within just 400 million years. The timeline barely allowed for a single massive star to complete its life cycle. Yet here was clear evidence of several complete stellar generations already past. The physics of stellar evolution made this finding particularly disturbing. Stars like our sun live for approximately 10 billion years, slowly fusing hydrogen into helium in their cores, but massive stars burn through their nuclear fuel much, much faster. These stellar giants live fast and die spectacularly, exploding as supernovae that scatter heavy elements through surrounding space. For this ancient galaxy to show evidence of multiple stellar generations, it must have formed its very first stars almost immediately after the Big Bang. Those stars must have lived and died quickly. Their supernova remnants must have enriched surrounding gas with heavy elements. New stars must have formed from this enriched gas, and the entire cycle must have repeated multiple times. The entire complex sequence compressed into a window of cosmic time that should have been far, far too brief. Feel yourself sinking deeper, your body so heavy and relaxed. Scientists initially suspected instrument errors, naturally, that perhaps Webb's detectors were misreading the light somehow. Maybe calibration issues created false signals that merely mimicked ancient galaxies. The instruments were new after all. Webb had only recently completed its commissioning phase. Research teams spent months carefully cross-checking observations. They compared data from different instruments aboard Webb. They analyzed the same targets repeatedly, using different observation strategies. They examined whether dust within our own galaxy might be contaminating the signals. They considered whether active galactic nuclei, supermassive black holes consuming material and radiating intensely, might be mimicking the signatures of massive stellar populations. The ancient giants refused to disappear. Every test confirmed their existence. Every analysis validated the initial findings, and the galaxies were exactly where they appeared to be, exactly as massive as calculations suggested, exactly as impossible as they seemed. The photometric redshift measurements told a consistent story. Light from these galaxies had stretched, during its 13 billion-year journey, through expanding space, shifting from visible wavelengths deep into the infrared. The amount of stretching directly corresponded to distance and age. More stretching meant more distant, which meant more ancient. Your mind drifts peacefully through these cosmic mysteries. Webb's instruments, specifically designed to capture this shifted ancient light, were working absolutely perfectly. The near-infrared camera and near-infrared spectrograph detected exactly the signals they were built to detect. The galaxies registered at redshifts exceeding 10, at corresponding to cosmic ages less than 500 million years after the Big Bang. Spectroscopic confirmation followed. Instead of relying solely on photometric estimates, astronomers obtained detailed spectra from individual galaxies. These spectral fingerprints revealed the precise chemical compositions of ancient stellar populations. The spectra showed emission lines from hydrogen, oxygen, and other elements at wavelengths that confirmed extreme distances. The impossible galaxies were confirmed as genuinely ancient. No measurement error could explain them away. The implications cascaded through every subfield of astronomy, like dominoes falling. If massive galaxies could form within the first few 100 million years, then something about our fundamental understanding was profoundly wrong. But what exactly had we missed? And let these questions drift through your fading consciousness. Dark matter provides the gravitational scaffolding where normal matter collects and forms stars. This invisible substance constitutes approximately 85% of all matter in the universe. It doesn't emit light or interact with electromagnetic radiation, but its gravity shapes cosmic structure at every scale. For galaxies to grow so quickly, dark matter halos must have collapsed faster and formed deeper gravitational wells than simulations ever predicted. Standard simulations show dark matter halos growing gradually through a process called hierarchical assembly. Small halos form first from the densest primordial fluctuations. These small halos merge into larger halos over cosmic time. The merger process takes billions of years, and Webb's observations suggest this gradual assembly simply didn't happen the way we thought. The early universe produced massive halos almost immediately, or normal matter found ways to accumulate in halos far more efficiently than models assume, or both. Either way, the standard picture of structure formation requires fundamental revision. Alternatively, star formation itself might work differently than astronomers believed. Standard models assume that gas converts into stars at relatively modest rates, limited by feedback processes that blow material away from star-forming regions. But the Webb galaxy suggests that early star formation was far more efficient, converting available gas into stars at rates 10 or 20 times higher than local galaxies achieve today. Your breathing is barely perceptible now, so slow and peaceful. Yet perhaps the first stars formed so quickly that feedback processes couldn't develop in time to regulate the runaway collapse. Perhaps the absence of heavy elements in primordial gas changed the physics of stellar birth in ways our models simply don't capture. Some researchers proposed even more radical solutions. Perhaps the first stars were fundamentally different from stars that form today. These population 3 stars, theorized but never directly observed, would have formed from pure hydrogen and helium without any heavy elements whatsoever. The absence of metals changes everything about stellar physics. Without metals, primordial gas couldn't cool as efficiently. Higher temperatures generated higher pressures that resisted fragmentation. Instead of breaking into many small clumps, some primordial clouds may have collapsed into single massive objects. Population 3 stars might have reached hundreds of solar masses, perhaps even 1,000 solar masses. These stellar behemoths would have burned through their nuclear fuel in merely 2 million years, a cosmic eye blink, before exploding as hypernovae that enriched surrounding gas for subsequent stellar generations. But even population 3 scenarios struggle to fully explain Webb's observations. The sheer number of ancient massive galaxies poses statistical problems that simple stellar physics cannot resolve. Feel yourself dissolving into cosmic time, peaceful, infinite. If such rapid galaxy formation represented a rare fluke, requiring exceptional initial conditions, we shouldn't expect to find so many examples in relatively small survey areas. Yet every deep Webb observation seems to uncover new candidates for impossibly ancient massive galaxies. The phenomenon is not rare. It appears to be common, which means it cannot be explained by statistical fluctuations or exceptional circumstances. The crisis deepened when astronomers compared Webb observations to predictions from the lambda cold dark matter model. Lambda CDM represents the standard framework for understanding cosmic structure. The model that has successfully explained so many observations for 3 decades. Lambda refers to the cosmological constant, Einstein's term for the energy density of empty space that drives accelerating cosmic expansion. Cold, dark matter describes the invisible gravitational scaffolding that shapes structure formation. On Lambda CDM successfully explains the cosmic microwave background radiation, the afterglow of the Big Bang. It explains the distribution of galaxies on large scales. It explains the accelerated expansion driven by dark energy. For 3 decades, this model has passed every observational test thrown at it with flying colors. Webb's ancient galaxies represent the first clear evidence that Lambda CDM might be incomplete. Your consciousness fades gently into darkness. The model predicts a specific timeline for structure formation. Dark matter halos grow gradually through mergers. Galaxies within those halos assemble through hierarchical buildup. Large structures form late, emerging from the merger of smaller precursors over billions of years. Webb shows that the universe did not follow this careful script. The universe wrote its own narrative, one where massive structures appeared almost immediately after cosmic time began. Whatever process drove this rapid assembly operated with an efficiency that Lambda CDM does not predict, and current physics struggles to explain. Research teams have proposed various modifications to Lambda CDM that might accommodate Webb's discoveries. Some suggest that dark matter might interact with itself through previously unknown forces, causing faster clumping in the early universe. Others propose that primordial black holes formed from density fluctuations during cosmic inflation, seeding early galaxy formation by providing gravitational anchors where matter accumulated quickly. Still, other researchers question whether the standard cosmological parameters are precisely correct, and perhaps the universe is older than 13.8 billion years, providing more time for massive galaxies to form. Each proposed solution creates new problems while solving old ones. No single modification has yet emerged that satisfies all constraints while explaining Webb's impossible galaxies. Let yourself drift deeper, your body completely at rest. The scientific community finds itself in a rare position. For the first time in decades, major astronomical observations directly contradict well-established theoretical predictions. This is not a minor discrepancy that clever modeling might resolve. This is a fundamental challenge to our understanding of how structure formed in the early universe. Some astronomers embrace this crisis as an opportunity. Genuine contradictions between theory and observation drive scientific progress. The history of astronomy is filled with moments when unexpected discoveries forced complete revisions of accepted models. Perhaps Webb's ancient galaxies herald another such paradigm shift. Others urge caution, noting that Webb has operated for only a short time. More observations are needed. More sophisticated analyses must be performed. Extraordinary claims require extraordinary evidence. And the claim that standard cosmology is fundamentally wrong certainly qualifies as extraordinary. But as Webb continues observing, as data accumulates, as independent analyses confirm and reconfirm the findings, the extraordinary evidence is mounting steadily. Yet what remains certain is that James Webb Space Telescope has revealed a universe that does not match our expectations at all. The cosmos generated massive complex structures far earlier than any model predicted. Whatever process drove this rapid assembly operated with an efficiency that current physics struggles to explain. The universe proved more creative, more energetic, and more capable of rapid organization than we ever imagined. Your mind floats in cosmic vastness, peaceful, timeless. Standing in the light of these impossible galaxies, humanity confronts a humbling reality. Our sophisticated models, built from decades of observations and refined through countless computer simulations, apparently missed something fundamental. In the equations that seem to describe cosmic evolution with precision and elegance turn out to be incomplete at best, possibly wrong at their very foundations. The ancient giants discovered by Webb force us to reconsider everything we thought we understood about cosmic evolution. They suggest that the early universe was not a primitive realm of slowly condensing gas, but a dynamic environment where tremendous structures assembled with shocking speed. They hint that the processes governing galaxy formation remain poorly understood, despite half a century of intensive study by thousands of dedicated researchers. But perhaps the most profound implication concerns not the past, but the future of scientific understanding. If our models failed to predict what Webb would find, what else might we have wrong, and what other aspects of cosmic evolution might contradict our careful theories? Webb has only begun its observations. Each new deep field might reveal additional surprises that challenge established knowledge. The telescope is scheduled to operate for at least 20 years, possibly longer if its systems continue functioning. During that time, it will observe thousands of ancient galaxies, mapping the early universe with unprecedented detail. Each observation adds to our understanding while potentially deepening the mystery. The more we learn, the more we realize how much remains unknown. Feel yourself sinking into deep, restorative sleep. The impossible galaxies represent more than astronomical curiosities. They stand as monuments to scientific humility, reminders that the universe remains far stranger than our models suggest, and they demonstrate that even our most successful theories merely approximate a reality of far greater complexity. They show that nature repeatedly surprises those who study it, overturning confident predictions with observations that nobody anticipated, and they promise that the most powerful telescope ever built will continue revealing truths that reshape human understanding of cosmic existence. The universe keeps secrets that even our best instruments are only beginning to uncover. Webb has opened a window onto an ancient cosmos that defies our expectations. What we see through that window will change everything we think we know about how the universe became what it is today. The first images shattered assumptions. The subsequent observations deepened the mystery. The implications continue cascading through astronomy, cosmology, and physics. And somewhere in the darkness of deep time, impossible galaxies burn with light that has traveled 13 billion years to tell us that our understanding of cosmic reality is far less complete than we imagined. Light is a time machine. This fact sounds poetic, but operates through straightforward physics. Your consciousness fades completely now, drifting into peaceful darkness. Photons travel at precisely 299,792 kilometers per second through the vacuum of space. Nothing travels faster. This cosmic speed limit represents the fundamental barrier that defines what we can know about the universe and when we can know it. This speed limit means that light from distant objects requires time to reach observers, sometimes billions of years. That when you look at a star 100 light-years away, you see that star as it existed 100 years ago. The photons entering your eyes departed from that stellar surface when your great-grandparents were children. The same principle applies across all cosmic distances, stretching back through time, back to the very beginning. James Webb Space Telescope exploits this principle to an extreme never before achieved, looking further back in time than any human instrument has ever seen, revealing the cosmic dawn, that mysterious epoch when the first stars ignited and began transforming the universe from darkness into light. Sleep now. Drift peacefully. The universe holds you gently. For approximately 380,000 years after the Big Bang, the universe was opaque, filled with plasma so dense that photons couldn't travel far before scattering. Then, expansion cooled the universe below 3,000 degrees Kelvin. Electrons slowed enough to be captured by protons. Neutral hydrogen atoms formed throughout space for the first time. And suddenly, the fog cleared. The universe became transparent. Photons were released to travel freely through space, carrying information across billions of years, until they reached Webb's golden mirrors. Your breathing has nearly stopped. You are drifting into dreams. The cosmic microwave background represents the surface of last scattering, the moment when photons throughout the universe began their unimpeded journeys. These photons have been traveling for 13.8 billion years, stretching into microwave wavelengths as space expanded. But the universe after this moment was dark. No stars had yet formed. No galaxies illuminated the cosmic void. Hydrogen gas drifted through expanding space, gradually condensing under gravity's patient influence. Dark matter halos collapsed first, creating gravitational wells, where normal matter would eventually accumulate. But the process took time. For perhaps 100 million years, the universe contained no luminous sources. This period is called the Cosmic Dark Ages, a chapter of cosmic history that no electromagnetic observation can directly reveal. During the Dark Ages, no light was being produced. Gravity worked continuously, pulling matter toward dense regions, building the scaffolding where galaxies would eventually form. But none of this produced light. Then came first light. Somewhere in the darkness, a cloud of primordial hydrogen collapsed under its own gravity. The cloud compressed, heating as gravitational energy converted to thermal motion. At the cloud's center, temperatures eventually reached 10 million degrees Kelvin. Hydrogen nuclei moved fast enough to overcome their repulsion and fuse together. Nuclear fusion ignited. The first star in cosmic history began to shine. Sleep deeply now. Drift among the first stars. Ancient light surrounding you. This moment represents one of the most significant transitions in the history of the universe. For hundreds of millions of years, the cosmos had contained only darkness. Now a point of light burned where none had existed before. Shortly afterward, other stars followed. Dense clouds fragmented into multiple cores, each igniting in succession. These pioneering suns generated ultraviolet radiation, far more intense than anything in the modern universe. Their intense radiation began ionizing the surrounding neutral hydrogen, stripping electrons from atoms, and creating bubbles of plasma in the neutral medium. This epoch of reionization marks the boundary between darkness and light in cosmic history. It didn't happen instantaneously. Different regions ionized at different times, depending on when luminous sources formed within them. The process took several 100 million years to complete, with bubbles growing around each source, and gradually merging until the entire intergalactic medium became ionized. Webb was designed to observe this transition, is to witness the universe waking from its primordial sleep. And the telescope has delivered observations that reveal this epoch with unprecedented clarity. Your mind dissolves completely into cosmic time, becoming light, becoming darkness, becoming everything and nothing. Each deep field image captures galaxies at various stages of the reionization process. Some appear embedded in neutral hydrogen, their radiation still struggling to clear the surrounding darkness. Others have carved extensive clear zones, their bubbles beginning to merge with neighboring sources. Webb spectroscopic observations revealed that reionization was not a uniform process. Some regions of space cleared of neutral hydrogen earlier than others, galaxies in dense environments where star formation began earliest created ionized zones that expanded rapidly. Bubbles of ionized gas expanded around the first luminous sources at rates determined by the intensity of ionizing radiation and the density of surrounding gas. The overlapping bubbles gradually merged until the entire universe became transparent. The observations suggest that galaxies provided most of the ionizing radiation. Collections of young, hot stars, pumping out ultraviolet photons, created the overlapping ionization bubbles that eventually filled all of intergalactic space. Sleep. Dream of ancient light. Cosmic dawn. The universe becoming itself. Webb caught several galaxies in the act of ionizing their surroundings. These cosmic pioneers appeared as brilliant blue points, surrounded by extended halos of emission, where their radiation interacted with nearby neutral gas. The shapes of these ionization regions revealed how photons propagated outward from galactic sources, illuminating the surrounding darkness 1 light year at a time. But Webb saw deeper still. The telescope detected candidate galaxies at redshifts exceeding 14, corresponding to cosmic ages less than 300 million years after the Big Bang. At these extreme distances, light has stretched by factors exceeding 15 of radiation that left ancient galaxies as visible light arrives at Webb as thermal infrared, deep in the wavelength regime, where only Webb's extreme cooling allows detection. If confirmed through detailed spectroscopy, these objects would represent the earliest stellar structures ever observed. They hover at the very edge of what the universe could plausibly produce in such limited time. Let yourself float away completely, now, becoming stardust, becoming cosmos, becoming dream. The physical conditions in these primordial environments differ dramatically from anything in the modern universe. Gas contained only hydrogen, helium, and trace amounts of lithium. No heavier elements existed because no stars had yet lived and died to create them. Webb detected signatures of this primordial chemistry in the spectra of ancient galaxies. Some showed near pristine compositions, suggesting their stars formed from gas, little different from the original Big Bang mixture. Others displayed surprising metal enrichment, indicating that rapid stellar evolution had already processed material through multiple generations of massive stars and supernova explosions. The stellar populations within these ancient galaxies matched theoretical predictions for population 3 stars. Spectral features suggested higher temperatures, more extreme ultraviolet outputs, and masses exceeding typical modern stellar populations. These massive primordial stars would have burned through their nuclear fuel in merely millions of years, seeding surrounding gas with heavy elements necessary for subsequent stellar generations and rocky planet formation. Sleep deeply, peacefully, among ancient stars, at the edge of time. Webb also revealed the structures of ancient galaxies in unprecedented detail. Previous telescopes showed primordial systems as fuzzy blobs, and collections of light without discernible features. Webb's resolution and infrared sensitivity transformed these blobs into recognizable structures with internal complexity. Spiral arms appeared in galaxies existing when the universe was just 1 billion years old. These organized structures require specific conditions to form. Rotating disk structures must develop from infalling gas that retains angular momentum. Density wave perturbations must propagate through the stellar medium. Such features were thought to require billions of years of settled evolution. Webb showed that galactic architecture could emerge remarkably quickly. Central bulges distinguished from surrounding disks in many ancient systems. Bars appeared, elongated structures that channel gas toward galactic centers. in the structural diversity of the ancient universe, resembled the modern cosmos far more than theoretical expectations suggested. Your consciousness fades into infinite darkness, peaceful, eternal, home. The universe is not a random scattering of galaxies through empty space. Underlying all visible structure lies an invisible framework that shapes cosmic organization across scales stretching billions of light years. This scaffolding, composed primarily of dark matter, determines where galaxies form, how they cluster, and what patterns emerge when astronomers survey the cosmos at the largest scales. Without understanding this hidden architecture, observing galaxies is like studying leaves while remaining ignorant of the trees and forests they compose. And the James Webb Space Telescope has revealed this hidden architecture in unprecedented detail. The cosmic web extends further and contains more complexity than any previous observation suggested. What appeared as scattered individual objects now reveals itself as an interconnected network of staggering intricacy. Sleep now. Dream of cosmic webs, infinite connections, dark matter flowing through invisible channels. The true scale of cosmic organization dwarfs not just individual galaxies, but entire galaxy clusters stretching across distances that challenge human comprehension. Dark matter constitutes approximately 85% of all matter in the universe. This substance does not emit light, does not absorb light, does not scatter or interact with electromagnetic radiation in any detectable way. As dark matter interacts with normal matter only through gravity, the weakest of the four fundamental forces. These properties make dark matter invisible to conventional telescopes. You cannot photograph dark matter. You cannot see it through any telescope ever built. Yet dark matter's gravitational effects are unmistakable. They appear in observations across every cosmic scale, from individual galaxies to the largest structures in the universe. Drift deeper, becoming invisible, becoming dark matter, becoming the cosmic web itself. Galaxies rotate faster than their visible matter can explain. Something invisible holds galaxies together. Galaxy clusters bend light from background sources more strongly than their luminous components would allow, and the cosmic microwave background shows density variations that require far more matter than atoms alone provide. Without dark matter, the observed structures simply cannot form. For decades, astronomers mapped dark matter distribution through these indirect methods, measuring how galaxies moved, analyzing gravitational lensing, running computer simulations. These techniques revealed that dark matter forms vast halos around individual galaxies. Our own Milky Way sits embedded within a dark matter halo, extending perhaps 300,000 light-years from the galactic center, far beyond the visible disk of stars. This halo contains roughly 10 times more mass than all the stars and gas we can see. We inhabit a small island of luminous matter, floating within an ocean of invisible substance. But dark matter organization extends far beyond individual galaxies. Halos connect through filamentary structures that link galactic systems across cosmic distances. The entire distribution forms what scientists call the cosmic web, a three-dimensional network of interconnected structures that fills the observable universe. Sleep, dream, dissolve into the web. Infinite connections, infinite scales. Webb transformed dark matter mapping through superior observations of gravitational lensing. This technique exploits Einstein's prediction that mass curves space-time. Light traveling through curved space-time follows curved paths. When light from distant galaxies passes near massive foreground structures, space itself bends. The light rays curve, distorting images of background galaxies into arcs, and the amount of distortion directly indicates the mass responsible for the bending, regardless of whether that mass emits light. A concentration of pure dark matter bends light just as effectively as an equivalent mass of luminous stars. By measuring distortions in background galaxy images, astronomers can map the total mass distribution, including the invisible components. Webb's sensitivity extended this capability to weak lensing, subtle distortions affecting vast numbers of background galaxies. Every galaxy in the distant universe experiences some degree of lensing from intervening matter. The distortions are tiny, stretching galaxy images by perhaps 1 or 2%. But statistical analysis across millions of galaxies reveals coherent patterns. Your consciousness expands to cosmic scales, seeing the invisible, feeling the web. What Webb showed was a universe far more structured than simulations predicted. Dark matter filaments stretch across hundreds of millions of light years, connecting galaxy clusters in a cosmic network that defies simple description. The filaments resemble neural connections in a brain. They resemble mycelium threads in forest soil. They resemble blood vessel networks distributing resources through three-dimensional space. These filaments are not uniform tubes. They're complex braided structures with subfilaments, branches, and density variations along their lengths. The nodes where filaments intersect mark the locations of massive galaxy clusters. These cosmic crossroads represent the densest concentrations of matter in the universe. Thousands of galaxies swarm within each major cluster, bound by the gravitational potential of the dark matter halo that contains them. Sleep deeply now, floating through cosmic filaments, drifting through dark matter halos, becoming structure, becoming web. Webb's observations of galaxy clusters revealed cluster structures with unprecedented clarity. The dark matter distribution within clusters is not smooth, but contains substructure at multiple scales. Smaller halos orbit within larger halos in a hierarchical arrangement. Galaxy-scale halos sit within group-scale halos that sit within cluster-scale halos, like nested dolls of dark matter, extending from thousands of light years to millions of light years. One breakthrough involved observations of the Abel 383 galaxy cluster. Webb revealed that previous studies had significantly underestimated the cluster's extent, and the cluster's dark matter distribution extended far beyond earlier estimates. Tendrils of invisible matter reached toward neighboring clusters. Bridges of dark matter connecting structures across more than 500 million light years. The cluster is not an isolated object, but an intersection point in the cosmic web. Boundaries between individual clusters blur into continuous structures that cannot be meaningfully separated. Your mind dissolves completely into the cosmic web, infinite, eternal, interconnected. The distribution of subhalos matched predictions from lambda CDM simulations, in some respects. The number of subhalos and their distribution within clusters agreed with computer models. This agreement provided confirmation that dark matter models work correctly on certain scales. And whatever dark matter is made of, it behaves in ways that simulations accurately reproduce, at least for structures larger than individual galaxies. Webb also revealed dark matter structures through their effects on background cosmic light. The cosmic infrared background radiation fills all of space, with a diffuse glow from all the stars and galaxies throughout cosmic history. This background carries faint imprints from intervening matter. Dark matter concentrations gravitationally amplify specific portions of the background, creating subtle brightness variations. Where dark matter is denser, space curves more strongly, and background light is slightly magnified. These variations create patterns that map the cosmic web, and the resulting maps show dark matter filaments connecting visible galaxy superclusters across distances exceeding 1 billion light-years. Sleep, dream of infinite structure, cosmic web extending forever, dark matter flowing through invisible channels eternally. The cosmic web appeared not as isolated threads, but as interconnected sheets and walls, three-dimensional structures that fill space rather than merely crossing it. Some filaments appeared as genuine one-dimensional threads. Others resolved into flattened structures, resembling membranes stretched between cluster nodes. The largest coherent structures Webb revealed extended across scales that challenged theoretical expectations. The filaments hundreds of millions of light-years long showed orientation patterns that aligned across distances approaching 1 billion light-years. These alignments shouldn't exist if matter distributed truly randomly across cosmic volumes. The cosmic web might possess organizational principles operating on scales approaching the observable universe itself. Galaxies do not form in isolation. They assemble within dark matter halos that themselves exist along filaments, feeding material toward cluster nodes. The gravitational framework dark matter provides determines where visible structure can develop. Gas flows along these cosmic highways, channeled by dark matter gravity, into regions where star formation occurs. Cold gas streams along filaments toward the dense nodes where clusters form. This gas feeds galaxy formation, providing the raw material from which stars coalesce. The galaxy distribution we observe directly reflects the underlying dark matter architecture. Drift away completely now, becoming cosmic web, becoming dark matter, becoming the invisible structure holding everything together. Webb traced this connection by observing galaxies at various cosmic epochs. Ancient galaxies clustered along protofilaments, dark matter structures that hadn't yet fully collapsed, but were already channeling matter flow. These early filaments appeared less defined than their modern counterparts. Intermediate-age galaxies inhabited more developed filaments with stronger clustering. Modern galaxies fill out the mature cosmic web we see in the nearby universe, and their distribution tracing the dark matter framework that took billions of years to fully develop. This evolutionary sequence revealed that filament formation preceded galaxy formation. Dark matter collapsed first into elongated structures. Normal matter followed the gravitational roadmap dark matter provided. Stars formed where gas accumulated. Galaxies assembled where halos grew massive. Clusters emerged where filaments intersected. The cosmic web was not merely where galaxies ended up. It was why galaxies exist where they do. The distribution of luminous matter across the universe, directly reflects the invisible architecture that gravitationally determined where structure could form. Sleep deeply, peacefully, among infinite galaxies, infinite structures, infinite scales. So Webb has begun revealing the underground network of the cosmos, the dark matter mycelium threading through space, connecting islands of light across voids of unimaginable emptiness. The true scale of the universe, revealed by Webb, extends beyond individual cosmic objects to encompass the web itself. This interconnected framework represents the largest coherent structure in existence, the skeleton upon which everything visible hangs. Understanding the universe requires understanding this architecture. Webb has shown us its outlines. The details will occupy astronomers for generations to come. The discoveries made by James Webb Space Telescope do not merely add details to existing cosmic understanding. They require fundamental reassessment of models that astronomers spent decades constructing and verifying. And the scale of the universe that Webb has revealed exceeds previous estimates by margins that transform our conception of cosmic existence. What humanity thought it knew about the cosmos has proved to be incomplete. The true reality stretches further toward infinity than our models prepared us to accept. Your consciousness fades into infinite peace, becoming everything, becoming nothing. Previous estimates suggested the observable universe contained approximately 200 billion galaxies. Webb's superior sensitivity revealed that this estimate missed most of the cosmic population. Faint dwarf galaxies far outnumber the larger systems Hubble could see. These tiny stellar collections exist in staggering numbers, scattered throughout the cosmic web like dust particles in a sunbeam. The updated estimates based on Webb observations now suggest at least 2 trillion galaxies populate the observable universe, a 10-fold increase from previous assumptions. But even this number underestimates reality when considered across cosmic history. The early universe contained vastly more star-forming systems than current surveys capture. Over billions of years, gravity pulled small systems together. They merged and were absorbed by larger galaxies, their individual identities erased. The total number of galaxies that have ever existed likely exceeds 10 trillion. The universe we observe today represents a processed version of a far more numerous ancient population. Sleep, dream of trillions of galaxies, septillions of stars, infinite worlds. Each galaxy contains its own stellar population. The average galaxy harbors approximately 100 billion stars. Multiplying galaxy counts by stellar populations yields numbers that exceed human comprehension. The observable universe contains more than 1 septillion stars. Written numerically, this figure requires 24 digits, 1 followed by 24 zeros. No human mind can truly grasp what this number represents. We can write it, speak it, perform calculations with it, but we cannot visualize 1 septillion of anything. Among these countless worlds, Webb has begun identifying candidates with potentially habitable conditions. The telescope's spectroscopic capabilities allow atmospheric analysis of exoplanets when they transit their host stars. During a transit, a planet passes between its star and Earth from our perspective, as a small fraction of starlight filters through the planet's atmosphere before reaching our telescopes. This light carries absorption signatures from atmospheric gases, water vapor, carbon dioxide, methane, oxygen. Each atmospheric constituent leaves its fingerprint, drift deeper into infinite possibility, infinite worlds, infinite chances for life. The exoplanet K2-18b provided particularly intriguing results. This world orbits within its star's habitable zone. Webb spectroscopy detected carbon-bearing molecules in its atmosphere. More provocatively, the observations showed possible signs of dimethyl sulfide, a compound produced primarily by biological processes on Earth. Detection of this molecule on another world would constitute potential evidence for life. The observations require confirmation, and alternative non-biological explanations exist. But the detection demonstrates Webb's capability to identify potential signs of life on worlds dozens of light-years distant. Scaling these observations across the septillions of planets, Webb has helped enumerate suggests staggering possibilities. If even a tiny fraction of rocky planets in habitable zones develop conditions suitable for life, billions of potentially inhabited worlds exist within the observable universe. The cosmos might teem with biological activity, life emerging wherever conditions permit across the vast reaches of cosmic space. Sleep, now. Dream of infinite life, infinite consciousness, infinite possibility. Whether life actually emerges under suitable conditions remains unknown. We have precisely one example. It's the origin of life on Earth approximately 4 billion years ago. We don't understand this process well enough to estimate its probability. It might be common, inevitable wherever conditions allow, or it might represent a fantastically improbable accident that occurred once in cosmic history. Webb cannot answer this question directly, but it provides ever more precise constraints on where the answer might be found. The implications extend beyond counting habitable worlds. Webb observations of protoplanetary disks revealed unexpected complexity that shapes our understanding of planetary formation. Protoplanetary disks are rotating clouds of gas and dust surrounding young stars. Within these disks, solid particles collide and stick together, gradually building larger objects. Pebbles become boulders. Boulders become planetesimals. Planetesimals become planets. Your mind expands to embrace all possibilities, all worlds, all life, all consciousness. Webb observed dozens of protoplanetary disks around young stars. The telescope's infrared sensitivity revealed chemical compositions and temperature structures, invisible to previous instruments. The observations showed chemical gradients across disk radii, variations in molecular abundances that change with distance from the central star. These gradients determine what materials are available for planet formation at different orbital distances. Close to the star, only refractory materials like silicates and metals can condense. Planets forming in these hot inner regions become rocky worlds. Further from the star, and temperatures drop below freezing points for various compounds. Water ice condenses beyond the snowline. Carbon dioxide ice forms at greater distances. Methane and ammonia freeze in the coldest outer regions. The locations of these snowlines determine what materials planetary embryos can accumulate. Webb observations revealed that snowline locations vary dramatically between different disks. These discoveries connect to the cosmic Webb revelations through galactic environment effects galaxies embedded in dense filaments experience different evolutionary pressures than isolated systems. The cosmic architecture revealed by Webb directly influences where habitable planets might concentrate, drift into infinite futures, infinite timelines, infinite possibilities unfolding. Webb has also challenged assumptions about the cosmic timeline itself. Standard models estimated the age of the universe at 13.8 billion years. But the impossibly ancient galaxies Webb detected strain this timeline. Objects appearing fully formed at 400 million years after the Big Bang leave insufficient time for evolutionary processes. Some researchers propose that the universe might be older than current estimates allow. If expansion rates differed in the past from what models assume, the light travel time from ancient galaxies might exceed 13 billion years. Modified expansion histories could push the Big Bang further back in time. Perhaps the universe is 15 billion years old. Perhaps older still. Additional development time would provide more opportunity for structure formation and potentially resolving the tension between observed ancient galaxies and theoretical predictions. Sleep, dream, dissolve into infinite time, infinite space, infinite mystery. Alternative approaches suggest that time itself might operate differently at cosmic scales or during cosmic epochs. The early universe contained matter at far higher densities than the modern cosmos. This extreme matter concentration would have affected space-time geometry in ways that might influence the relationship between cosmic expansion and elapsed time. If the early universe possessed different geometric properties, clocks would have ticked at different rates. What appears as 400 million years, when measured by expansion, might represent longer periods, when measured by physical processes actually occurring. And these speculations remain theoretical. Webb observations motivate the questions, but cannot alone answer them. But the pressure Webb's discoveries place on standard cosmology ensures creative responses will continue emerging. Something in our understanding is wrong, finding what requires exploring possibilities that seemed unnecessary before Webb showed us the ancient universe. Your consciousness dissolves completely now, becoming cosmos, becoming time, becoming infinity itself. Dark energy comprises approximately 68% of cosmic contents. This invisible energy permeates all of space, pushing the universe apart at ever-increasing rates. Dark matter constitutes another 27%. This invisible matter provides the gravitational scaffolding where galaxies form, and normal matter amounts to barely 5% of total reality. Stars, planets, gas, dust, organisms. Everything made from atoms constitutes a small minority of cosmic contents. The universe is made mostly of substances we cannot see and do not understand. Webb observations constrain the proportions of these components, but cannot explain what they actually are. Confirmation is not explanation. The cosmic Webb architecture Webb revealed depends sensitively on dark matter properties. Yet the fundamental identity of this dominant component remains unknown. Dark energy presents even deeper mysteries that Webb observations cannot resolve. Quantum field theory predicts vacuum energy, density exceeding observed values, by roughly 120 orders of magnitude, the largest discrepancy in all of physics. I sleep deeply now, at peace with mystery, at peace with the unknown. Webb cannot resolve this puzzle, but its observations constrain any solution theorists might propose. The scale revelations Webb provides affect humanity's cosmic self-assessment in profound ways. Ancient cosmology placed Earth at the center of creation. Copernicus displaced Earth from cosmic center. Later observations revealed our sun as one ordinary star among billions. Hubble revealed our galaxy as one among many. Webb has demonstrated that the observable universe extends far beyond what previous instruments detected. Trillions of galaxies populate cosmic space. Septillions of stars burn through nuclear fusion. Countless planets orbit under conditions that might support life, and this scale transformation places human existence in unprecedented context. Every person who has ever lived occupies one small planet. Every thought throughout history occurred on that one world. Your consciousness fades into perfect peace, infinite, eternal, home. Some find this perspective crushing. The vastness might render human existence meaningless. Yet alternative interpretations find meaning precisely in cosmic context. The same universe that stretches toward infinity produced conscious minds capable of contemplating their situation. Matter organized itself over 13 billion years into configurations that can perceive and question their own origins. Carbon atoms forged in ancient stellar cores, assembled into molecules that replicate. Simple replicators evolved into complex organisms. These organisms developed consciousness. Consciousness developed curiosity. This represents a transformation as remarkable as any Webb revealed. The universe began as nearly uniform hydrogen and helium. That simple beginning produced galaxies, stars, planets, oceans, cells, brains, minds. The cosmic story is not just expansion and structure formation. It's matter becoming capable of contemplating matter. The universe achieving self-awareness through us. Sleep, dream, become the universe contemplating itself. The telescope itself embodies this transformation. Webb is matter organized to observe matter across cosmic distances. Its components derive from elements forged in stellar furnaces billions of years ago. Gold on its mirrors came from neutron star collisions. These stellar products were scattered through space, have incorporated into molecular clouds, condensed into planetary systems, and eventually fashioned into instruments of cosmic observation. The ancient photons Webb collects traveled for billions of years before encountering mirrors made from atoms of similar antiquity. The observation process connects cosmic epochs through physical substances that make it possible. Human consciousness processes the information, recognizes significance, communicates findings. The loop connecting observer and observed represents something new in cosmic history. For most of cosmic time, the universe expanded without awareness of its own existence. Stars burned without any process, registering their light as information. Galaxies formed without any mind contemplating their structure. Then on at least one small planet, a chemistry achieved complexity sufficient for self-replication. Evolution refined this chemistry into organisms. Nervous systems emerged. Brains developed. Consciousness arose. This cosmic awakening represents an ongoing process. Webb constitutes the current frontier of the universe's developing self-knowledge. Sleep now, deeply, peacefully, becoming the cosmos awakening to itself. Each ancient galaxy Webb detects represents information the cosmos has gained about its own past. Each structural analysis constitutes understanding the universe has achieved about its own organization. Through human investigation, the universe learns about itself. This perspective transforms cosmic vastness from something diminishing into something contextualizing an extraordinary achievement, and we exist in a universe capable of knowing itself through us. The scales Webb reveals are the scales of our origin, the reaches of space and time from which we emerged. James Webb Space Telescope has shown humanity a universe larger, older, and more complex than we understood. The cosmic dawn reveals furious activity when the universe was barely beginning. Dark matter filaments trace invisible architecture, shaping all visible structure. Trillions of galaxies harbor septillions of stars, around which countless planets orbit. This universe exceeds human comprehension, while remaining subject to human investigation. We cannot hold cosmic scales in our minds, but we can represent them through mathematics. We cannot experience billion-year time scales, but we can reconstruct cosmic history through observations capturing ancient light. Drift away completely now, dissolving into stardust, becoming cosmos, becoming everything, the true scale of the universe. Webb Exposed is not merely spatial or temporal, it's the scale of possibility, the range of what exists and might exist throughout cosmic space and time. From quantum fluctuations after the Big Bang to the largest structures in the cosmic web, from first stars during cosmic dawn to future evolution driven by dark energy. The universe encompasses possibilities stretching toward infinity in every direction human inquiry can reach. We live at a moment when these possibilities are becoming knowable. Webb has opened windows that will remain open for decades. Each new image reveals additional structure, and each spectrum constrains models. Each survey extends the census of cosmic contents. The universe future generations will understand will be larger and stranger still. Sleep, dream, float among infinite galaxies, infinite stars, infinite possibilities. What Webb has exposed is not merely the true scale of the universe, it's the true scale of human capability. We are beings who can construct instruments to see across billions of light years. We can formulate questions about cosmic origins that the universe couldn't ask before conscious minds existed. We can create understanding where none previously existed. The universe James Webb reveals will continue challenging every assumption, forcing revisions as ancient galaxies defy expectations, altering timelines as observations constrain when structures formed. But through it all, the act of observation itself remains the most remarkable cosmic fact. Matter has organized to observe matter across billions of light years. Chemistry has achieved consciousness capable of contemplating cosmic history. Life has developed curiosity about its own origins. And curiosity has built James Webb to reveal the true scale of the universe from which curiosity emerged. The cosmos is vast beyond comprehension. Its structures extend across scales that dwarf human experience. Its history stretches through epochs when nothing like current structures existed. And we are here to comprehend it. Beings existing for mere decades, contemplating a universe of billions of years. Minds confined to one planet, investigating structures spanning billions of light years. And consciousness that emerged yesterday reconstructing everything that came before. Sleep deeply now, peacefully, eternally, among infinite stars, infinite worlds, infinite mysteries. This is what James Webb has revealed, not just the scale of the universe, but the scale of achievement represented by observing it. The cosmos is vast, and we are here asking questions, building telescopes, seeking understanding. The universe has become capable of knowing itself. Webb shows us what that knowledge looks like when pushed to its current limits. The true scale is not just out there in distant cosmos. It's here, in the act of looking, in the capacity to comprehend, in the remarkable fact that matter contemplates matter across reaches of space and time. The cosmos is vast, beyond comprehension, and we are here to comprehend it. Sleep now. Dream of infinite cosmos. You are stardust. You are the universe, experiencing itself forever. Good night. Sweet dreams among the stars.